Hello, dear students. Today we will start another topic that is about reduction of data, that is data compression. So, data compression is the reduction in the little amount of signal space that must be allocated to a given message or data sample set. The sample space could take the form of a physical volume such as a data storage or a magnetic tape or in a RAM, an interval of time during which a given message is to be transmitted, or it could be bandwidth required by a signal to be transmitted. All these forms of signal space, that is volume, time and bandwidth, are interrelated by the equation. As you can see, volume is equal to function of time and bandwidth, or we can say time into bandwidth. Any reduction in volume of signal space can be related to reduction in time or bandwidth. Now, what is the need for data compression? To meet an operational specification under an existing system performance, such as limited bandwidth, interval of transmission, or etc. It can be also to save cost in the operation of the system. A typical computerized medical signal processing system requires a large amount of data that is difficult to store, process, and transmit. The data has considerable amount of redundancy associated with it. So it is required to achieve maximum data volume reduction while preserving the significant signal morphological features so that they can be obtained after reconstruction. Now what we will make this topic specifically first for ECG. So what is the need to compress the ECG data? ECG data is often to be stored for subsequent comparison and evaluation. It may sometimes be required to be transmitted in real time. In ambulatory care needs implementation of rhythm algorithms in real time. In telemedicine, it requires economical and rapid transmission of the acquired waveform to a remote interpretation center. In both, ECG monitors and recording requires improved functionality since computer hardware can be utilized to analyze the waveform in real time and store the results and further display examples of if any abnormality found. Now, what is the performance measure? How we can measure that this reduction technique is better or not? So first is in that reduction ratio. It is the ratio of number of bits of the original signal to the number of bits that are saved in compressed signal. Next is the visual inspection. In biomedical reduction, we usually determine the clinical acceptability of the reconstructed signal through visual inspection. Then is a numerical measure. If you see this equation below, so that is the percentage root mean square difference, that is PRD. So that measure the residual, that is the difference between the reconstructed signal and the original signal, and it can be computed as you can see in the equation. PRD is equal to whole under root. We have summation I is equal to 1 to n x original value, original data minus the reconstructed data whole square divided by summation I running from again 1 to n original data square. So here n is the number of samples, and as I said, x ORG, that is the original sample or data sequence, and XREC, that is the reconstructed data sequences. A lossless data reduction algorithm produces zero residual, and the reconstructed signal exactly replicates the original signal. However, clinically acceptable quality is neither guaranteed by a low non-zero residual nor ruled out by a high numerical residual. Now, what are the different ECG data compression techniques? There can be direct data compression, transformation methods. So these methods belong to the lossy class of algorithms, and we will keep our main focus on these techniques. They retain important information about the signal, but they discard the rest. And they produce residuals that are non-zero, as I mentioned, because these are the lossy class of algorithms. And lossless techniques include Huffman coding, variable encoding. These, I think you people have already studied these techniques. Now we'll start with the direct ECG data compression techniques, and the first one in this is turning point, or we can say TP algorithm. The important consideration in the development of the TP algorithm is the QRS complex. The technique have the potential to reproduce QRS complex with as near fidelity as possible when the compressed data is used to reconstruct the signal. It is very simple in construction and yields a compression of 50%, except where the signal alternates between a peak and a trough. In the monitoring scenario where the highest frequency is assumed to be around 50 Hz, roughly we can say that it corresponds to the QRS complex, and a sampling frequency of 200 Hz, the turning point algorithm will produce a method of efficiently reducing the effective sampling rate by at least one half, that is 100 samples per second. Now let's see how it works. So the algorithm considers three sample points at a time. It retains the first sample by assuming it as a reference point, that is x0, and the next 2 points are designated as x1 and x2. The algorithm then decides whether to retain x1 or x2 depending upon which of the 2 points best conserves the turning point of the signal. You can see in this figure, it shows various patterns of this triple x0, x1 and x2. So in each frame, the encircled point preserves the slope of original 3 points. The algorithm retains this point and makes it to the reference point x0 for the next iteration. It continues to sample the next two samples by assigning them as x1 and x2 and repeats this process. Now you can note this except in the case of patterns 1 and 2, when there is a turning, it is always the last point x2 that is stored. In case of a turning, x1 is retained. So you can see here this x1 and x2 because it is a complete change in slope. So in this case x1 is retained, otherwise we have x2 which is retained. As it is not possible for a computer to visually inspect the various patterns and determine which point is to be stored, a mathematical relationship is developed. So this is we'll see the mathematical relation. So for that, we should know what this signum function is. So if we have a signal or sequence x, so signum function of that is given as 0 if that is 0, plus 1 if it is greater than 0, and minus 1 if it is less than 1. So here we will keep two points or parameters that are S1 and S2. So S1 is computed as signum function of x1 minus x0, and S2 is computed as signum function of x2 minus x1. So here S1 and S2 basically are the slopes of the two consecutive points, and if the difference of either x1 minus x0 or x2 minus x0 is 0, it will produce a 0 result. Now you can see this table 2, it shows the signs of patterns corresponding to 9 configurations of table 1, so as well as the choice of the retained point. So we have seen if it is a turning plus to minus 1 or minus, you can see this, so we have retained the point x1, it is you can see minus 1 to 1 or 1 to minus 1, so we have retained this point x1. Otherwise we have either plus 1 to 0 or 0 to minus 1, or if it is this is the same, so we'll retain the point x2. Now this is a flow chart to implement a turning point algorithm. So you can see first we have to initialize I, we have to take xi, means first you will take x naught, and then accordingly we will move to next, like x naught is xi, then we'll choose two further points x1 and x2. We'll continue compute s1 and s2, then we will check the sign of s1 s2. If it is not less than 0, then we'll store x2 and we'll move 2 points further, and if it is less than 0, we have to store x1 and we have to move 1 point further. So that is the process. Now what is the advantage of turning point algorithm? It is fast and simple to implement. It produces a compression ratio of 2 is to 1, and it can be implemented in real time as original signal can be reconstructed from the compressed data by suitably interpolating between the saved data points. The algorithm can be applied a second time to the already compressed data, yielding a compression of 4 is to 1. Now, what is the limitation of this method? The algorithm is likely to introduce non-trivial distortion. For instance, if the original ECG signal is sampled at 200 and its acquired bandwidth is 50 Hz, then we will be virtually sampling at a frequency less than the highest frequency, that is 50 Hz, for which unique reconstruction is not guaranteed. In this method, the saved points are not uniformly spaced in time, which introduces short time distortion. Now let's see some examples of this TP algorithm. So we have three different ECG waveforms corresponding to this is normal sinus rhythm. Then we have the waveform corresponding to tachycardia, and this is PVC. So the waveforms were sampled at 1000 Hz, and the TP algorithm applied once and second time to the sampled sequence. So this 1, 2, 3 will show original waveform and then reconstructed. These are the reconstructed waveforms after we applied TP algorithm once and twice, so that is number 2 and number 3. Now the next algorithm is amplitude zone time epoch coding, that is AZTEC algorithm. Data compression algorithm for both ECG monitor and databases. It is capable of high compression ratio for the order of 10:1, and it takes the raw ECG data and converts it into short lines, and we call them as plateaus and slopes. The algorithm consists of two parts. The first is which deals with the line detection, and the second deals with line processing. So let's start with the line detection. This operation is carried out by the use of zero-order interpolation to produce horizontal lines. You can see in this figure, so it shows the line detection operation using zero-order interpolation. So we have to start. So first we have to choose the maximum and the minimum value. You can see then we have to initialize plateau. We will first go to line 1 and will initialize CAZT variable, that is equal to 1. So then we will wait for the next sample, and we'll choose next point, means with what will be that ECG point, maximum point, minimum point, and we will we will increment that length to 1. Then we will see if it is greater than 50. Then we have to we have to go to the final situation where we have to decrease this NUM number by 1, and we have to choose V1 again. And then we will move to A, that I will show in the later slides what is this A and B. And if it is not greater than 50, then V maximum will be less than V. If it is not so, then we have to move further. If it is greater than V, if it is not, or yes, we have to choose. If it is greater than V, we have to initialize this V minimum as V, and if it's not, then we have to choose a threshold, that this difference Vmaxi minus V minimum should be less than this threshold. If it is not less than, then again we have to compute the new V1 point, and if it is less than, then we have to go to point B. So two variables, as I mentioned, Vmax and Vmin, always reflect the highest and lowest elevations of the current line. And as I said, this line length keeps track of number of samples examined. A plateau is stored if either the difference between Vmxi and Vmin is greater than a predetermined threshold, that is Vth, or if line length is greater than 50. So the stored values are the length, that is line length minus, we can say, 1, and the average amplitude of the plateau will be Vmxi plus Vmin by 2. So figure B, this is, you can see the A point where it is attaching this one. So this shows the line processing algorithm. So for it was line detection, now it is line processing, which either produces a plateau or a slope depending on the value of variable line mode. So we initialize this line mode, you can see, to this plateau in order to begin by producing a plateau. The production of an AZTEC slope begins when the number of samples needed to form a plateau is less than 3. So setting line mode to slope indicates that we have entered slope production mode. Then determine the direction or sign of the current slope by subtracting the previous line amplitude V1 from the current amplitude VSI. Also, reset the length of the slope TSI. The variable VSI records the current line amplitude so that any change in the direction of the slope can be tracked. We can note here that VMXI and VMNI are always updated to the latest sample before the line detection begins. So this forces ZOI to begin from the value of the latest sample. So when the program reverts to line processing with line mode equal to slope, either the slope is saved or updated. So it is saved either when a plateau of more than 3 samples can be formed or when a change in direction is detected. If a new plateau of more than 3 samples is detected, then the current slope as well as the new plateau is saved. For the slope, the stored value are its length TSI and its final elevation, that is the amplitude of the last sample point V1. As both slope and amplitude are saved as numbers, TSI is multiplied with -1 to differentiate a slope from a plateau, that is, the minus sign serves as a flag to indicate a slope. The length and amplitude of the new plateau are saved. All the parameters are then reset and the program is initialized to plateau detection. If a change in direction is detected in the slope, first save the parameters for the current slope and then reset sign VSI, TSI and VMXI and VMNI to reproduce a new AZTEC slope. Now the algorithm returns to the line detection but remains in the slope production mode. When there is no new plateau or change of direction, simply update the slope parameters, that is TSI and VSI, and return to line direction with line mode remaining set to slope. Let's see an example. So this figure illustrates the ECG signal and its representation using AZTEC. So figure A shows the ECG waveform which is sampled at 500 samples per second, and the second is the AZTEC representation. So it has the advantage of online smoothing, data reduction and coding. This does not produce a constant data reduction ratio. The ratio is frequently as great as 10 or more, depending on the nature of the signal and the value of the empirically determined threshold. AZTEC method of line slope coding permit a rapid search of the stored data to locate the QRS complexes. Now, data reconstruction. How you use to reconstruct the data after doing compression. The data array produced by the AZTEC algorithm is an alternating sequence of durations and amplitudes. So as you can see, we'll just understand this with an example. So this is a AZTEC coded data you can see. So I'm just keeping these points, means we can see this values 15, then we have 80, 5, 100, -8, -200, -5, 150, 25, 150. So how these data we are using now to reconstruct the original signal. So the reconstruction can be done by expanding the plateaus and slopes into discrete data points. In this example, if you see the first 2 points in the sequence like 1580, what they represent? They represent a line length that is of 15 samples and it will be of amplitude 80. So you can see we have drawn this up to 50 here, 15 here, this line which has the amplitude of 80. Now the second set of two samples, as you can see, we have 5 and 100. So that will represent again another segment of 5 samples, as you can see in this graph. So 5 samples, these are 5 samples means up to 20 of constant amplitude 100. So this is up to 100. Now third value, if you see, that is a negative. If you see here, this third value is negative, it is -8 and then it is -200. So that means this -8 represents, now it represents a line segment with non-zero slope. There is no zero slope. So this line is 8, means that will indicate a slope, not a plateau. So this line is 8 samples long, that is -8. But how much will be the amplitude? Beginning at the end of the previous line segment, that is 100 amplitude, and ending at an amplitude of -200. So that is a slope which will start from +100, will move to -200, but samples, how many it has to complete? It has to simply complete 8 samples. Now next value is also a line with non-zero slope beginning at an amplitude of -200, ending with an amplitude of +150 after 5 samples. So you can see this is now 5 samples. You have 150 amplitude, but that is now a plateau. So it will be having a constant amplitude. The last set of values represent a horizontal plateau of 25 samples with an amplitude of 150. So this is how we can reconstruct the compressed data using AZTEC algorithm. This reconstruction process produces an ECG signal with step-like quantization which is not clinically accepted. So this AZTEC encoded signal needs post-processing with a curve smoothing algorithm or a low-pass filter to remove its jagged appearance. The least square polynomial smoothing filter, which means it is according to literature, is an easy, fast method for smoothing the signal. This family of filter fits a parabola to an odd number, that is 2l+1 of input data points. Now let's suppose we are taking this L equal to 7. So we obtain these data points, as you can see, 1 by 21 whole bracket minus 2xk minus 3 plus 3xk minus 2 plus 6xk minus 1 plus 7xk plus 6xk plus 1 plus 3xk plus 2 plus 2xk plus 3. So here xk is the new, that is smooth data point, and x small xk plus minus n are the original AZTEC data points, and k plus minus n define the time relationships. The smoothing function acts as a low-pass filter to reduce the discontinuities. Now let's see one more illustration. Again, we are considering three different ECG waveforms. So this is normal sinus rhythm, a rhythm which is reduced as 170 by 100. Tachycardia, this is B part. Again, data reduction of 340 to 100. And PVC, that is data reduction of 132,000. So first is showing the original, second is showing the AZTEC coded ECG waveform, and third one, basically these are reconstructed ones, and third one is after smoothing with a parabolic filter. So disadvantage of smoothing process is the loss of amplitude morphology. This amplitude information is important in the detection of disorders of the ventricles such as ventricular hypertrophy. So this is all in this lecture. We'll continue the data compression techniques in next lecture also. So